Welcome to the deep dive. Imagine stepping into medical school, that exhilarating but also pretty overwhelming feeling.
Oh, yeah.
It's like trying to drink from a fire hose, right? You're not just looking for facts, you're craving true understanding, a structured approach to learning that actually sticks, and maybe those aha moments that make everything click.
Exactly.
Okay, let's unpack this. That's precisely what this deep dive is all about. Our mission today is to give you a comprehensive yet engaging understanding of tissues of the body. Think of this as your foundational course, a shortcut designed specifically for you, a first-year medical student, to cut through the complexity. We're not just defining tissues, we're diving into why they matter, how they build, how they communicate, and crucially, how they sometimes fail.
Right.
Our goal is to arm you with a clear framework and the most important nuggets of knowledge you'll need to really understand and retain this vital information.
What's truly fascinating here is how we can take such a vast topic and, well, simplify it. We'll focus on the core principles and immediately connect them to real-world clinical implications.
So linking it straight away.
Yes, this approach helps create those aha moments from the very beginning, giving you a conceptual framework that will serve as like the alphabet for your entire medical career.
So how are we going to build this understanding layer by layer, just like the body itself? We'll start by exploring the tools and foundations that let us see the invisible cellular world. Then we'll get acquainted with the 4 basic tissue types, nature's fundamental building blocks. From there, we'll move into their clinical relevance, examining what happens when these tissues go wrong.
Which is key.
Absolutely. We'll then switch gears to membranes and excitability to understand how cells communicate electrically, before zooming out to internal linings in early development to see how the body takes shape from its very beginnings.
Right, the bigger picture.
And finally, we'll wrap up with histopathology and disease mechanisms to understand exactly how tissues fail and how the body attempts to repair them. It's a holistic journey designed to give you a clear, connected view. Module 1, Tools and Foundations. Seeing the invisible. Okay, let's jump right into Module 1, Tools and Foundations, Seeing the Invisible. We're starting with the fundamental unit of life itself, the cell. Now imagine each cell not just as a blob, but as a miniature, highly organized city.
That's a great analogy.
Every city has its own specialized departments or organelles, all working together in, well, perfect synchronicity. It's a marvel of microengineering. And while a skin cell might look vastly different from a neuron, they actually share much of the same internal machinery and organizational principles.
Indeed. And every city needs a protective boundary, right?
Yeah.
Which brings us to the plasma membrane, the city wall and guarded gates.
Yeah.
The crucial insight here is that this isn't a static barrier. Think of it as a dynamic, intelligent border, constantly regulating what comes and goes and how the cell communicates with its environment. It's composed of a fluid mosaic of fats and proteins, a phospholipid bilayer that's always in motion, embedded with integral and peripheral proteins that act as channels, pumps, and receptors.
Those are the gates you mentioned.
Exactly. They're the gates and communication hubs, controlling traffic and receiving signals. Cholesterol helps regulate its fluidity, and carbohydrate chains on the surface act like ID tags for cell recognition.
So it's not just a simple fence, it's the entire security system and communication hub rolled into one. And when that complex system fails, we see very real consequences, right?
Absolutely. For instance, sometimes the internal scaffolding just beneath the plasma membrane, made of proteins like spectrin and ankyrin, can be defective. This leads to conditions like hereditary spherocytosis, where red blood cells lose their normal flexible shape, becoming fragile and spherical.
Right, they can't squeeze through capillaries easily then.
Precisely. They're then prematurely destroyed, illustrating that weak scaffolding equals fragile walls, and the city crumbles. This shows you immediately how a structural defect at the cellular level translates directly into a clinical problem. Moving inward, we come to the nucleus, the city hall and library. This is typically the largest and most centrally located organelle, enclosed by a double-membrane nuclear envelope with crucial nuclear pores for controlled passage of molecules.
So the control center.
Exactly. It's the cell's control center because it stores all the genetic instructions, the DNA, organizes chromatin. We can even tell how active a cell is by looking at its nucleus. Euchromatin, which stains lightly, is like open books. It's transcriptionally active, meaning genes are being read.
Okay.
Heterochromatin, dark and dense, is like closed books, transcriptionally inactive. Within the nucleus, a darker spot, the nucleolus, is where ribosomes, the cell's protein-making factories, are synthesized.
Got it.
So it stores all laws, DNA, decides which to read and act on transcription, and sends out orders, mRNA, to the factories.
And even this central command unit can have issues. Defects in nuclear envelope proteins, known as laminopathies, can disrupt its structure, leading to rare but severe conditions like progeria, a premature aging syndrome.
Yeah, it's quite devastating.
It's a powerful reminder of how fundamental the integrity of the nucleus is. From the nucleus, we extend into the endoplasmic reticulum, or ER, these are the factories of our cellular city. We distinguish two types. The rough ER, our ER.
Rough because of the ribosomes, right?
Exactly. It's a network of membranes studded with ribosomes, those little protein-making machines. Its main job is to synthesize proteins, especially those destined for secretion or insertion into membranes. It also has a critical quality control role for misfolded proteins. Think of the RER as the protein factory line. Then there's the smooth ER, SER, which lacks ribosomes, giving it a smooth appearance. The SER is incredibly versatile, acting as the lipid refinery, detox center, and calcium warehouse.
Very diverse function.
Totally. It synthesizes lipids and steroids, detoxifies drugs and harmful compounds, especially in liver cells, and stores calcium, which is vital for muscle contraction.
Right. And once those proteins and lipids are produced, they need to be processed, sorted, and sent to their correct destinations. That's the job of the Golgi apparatus, the cell's post office. It's a stack of flattened sacks that modifies, sorts, and packages proteins and lipids into vesicles, like little transport parcels, directing them for secretion, integration into the plasma membrane, or delivery to other organelles.
Like sending out mail.
Imagine parcels being stamped, labeled, and sent to the right address. The Golgi is meticulously efficient. The Golgi's role even spills over into something as complex as cancer.
Really? How so?
If it starts processing glycoproteins abnormally, that can actually help tumor cells invade and even hide from the immune system. It's a subtle but incredibly critical factor in how cancer progresses.
Wow. Okay, and what about cleanup and energy for this bustling city? That brings us to lysosomes and peroxisomes, the recycling and waste management department. Lysosomes are acidic vesicles packed with digestive enzymes, essentially the recycling plants of the city, breaking down worn-out organelles, pathogens, and cellular debris for reuse.
Very important for keeping things tidy.
And peroxisomes are the detox hubs, neutralizing free radicals and breaking down fatty acids. When these systems fail, the city gets choked with waste. Take Tay-Sachs disease, a devastating lysosomal storage disorder where a crucial enzyme is missing, leading to a toxic buildup of lipids in neurons.
Tragic consequences.
This causes progressive neurodegeneration, illustrating that the recycling plant shuts down, waste piles up, and poisons the city.
And no city can run without power, which brings us to the mitochondria, the power stations. These organelles are the primary site of oxidative phosphorylation, producing ATP, truly the currency of energy for the cell.
Can't do anything without ATP.
Exactly. No power, no city. ATP is essential for every process. What's particularly interesting is that mitochondria have their own DNA and ribosomes and reproduce independently, even being maternally inherited.
That's the endosymbiotic theory connection, right?
Precisely. This unique biology means that when these power stations malfunction, as in mitochondrial myopathies, it leads to defects in ATP production, causing muscle weakness, seizures, and lactic acidosis.
Finally, every city needs its infrastructure, and that's the cytoskeleton, the cell's roads, scaffolds, and cranes. This dynamic network of protein filaments gives the cell its shape, allows movement, and provides tracks for internal transport. The main components are actin filaments, like sidewalks and temporary detours for cell shape and movement, intermediate filaments, the steel beams providing tensile strength like keratin and skin cells, and microtubules, the highways with trucks for transporting cargo and forming structures like cilia.
A really complex internal network.
And if one of these components is faulty, the whole system can suffer. For instance, mutations in keratin can cause blistering skin disorders like epidermolysis bullosa, or skin blisters with even minor trauma, showing that when one department fails, disease results. To really solidify this, remember the cell as a mini-city metaphor. Understanding the precise function of each organelle is absolutely critical for recognizing and diagnosing disease when one department fails. It's the microscopic basis for everything you'll study.
Building on that understanding of the cellular city, Module 1B takes us to light microscopy, mapping the microworld. Histology, as you'll learn, is simply the study of tissues under a microscope. It's about needing special tricks to make cells visible.
Right, they're mostly clear otherwise.
Exactly. Imagine the human body as a giant Lego city. Microscopy is that zoom lens, letting us examine the tiny Lego blocks the cells and their arrangements.
And to get those clear images, we follow a precise, almost artistic process. It starts with a biopsy, getting a small tissue sample. Then, fixation with formalin preserves cell structure. It freezes the tissue in time.
Stops everything decaying.
After that, the tissue is embedded in paraffin wax for support, allowing ultra-thin slices to be cut in sectioning with a microtome. Finally, staining with dyes makes the structures visible for microscopy. Think of it like preserving, slicing, and coloring a fruit to study its inside clearly.
The staining process reveals so much. The most common is hematoxylin and eosin, or H&E. Hematoxylin stains acidic structures like DNA, our blueprints, blue-purple, primarily coloring the nuclei.
The blue bits.
Right. Eosin stains basic proteins, the brickwork in the cytoplasm, and extracellular matrix pink red.
The pink bits.
The pink bits. Beyond H&E, other techniques provide specific insights. For instance, immunohistochemistry, IHC, uses antibodies to detect specific proteins, like cancer markers. It's like testing if a tumor has a lock that can be opened by a specific key, which could be a targeted drug.
Super useful for treatment decisions, then.
Absolutely essential.
Once those slides are prepared, microscopic interpretation becomes a crucial skill. Recognizing colors, shapes, and patterns helps pathologists differentiate healthy, stressed, or diseased cells. Even the nucleus, as we mentioned, tells a story. A pale nucleus with visible nucleoli suggests an actively synthesizing cell. Busy factories look lit up.
Active.
A shrunken dark nucleus, or pynotic nucleus, indicates irreversible injury. The library lights are off forever.
Clinically, histology is essential. It's critical for cancer grading, differentiating aggressive tumors from less aggressive ones. It helps identify the cause of injury, like distinguishing between apoptosis and necrosis. We often use frozen sections for rapid diagnosis during surgery, like checking tumor margins.
A quick look.
Yeah, they're a quick sketch map compared to the detailed blueprint of permanent sections, which are the gold standard.
Ultimately, microscopy is the camera of biology, capturing snapshots of life at the cellular level, making it an indispensable tool for diagnosis and understanding the microscopic basis of health and disease. Module 2, the 4 basic tissue types, nature's building blocks. So we've peered inside a single cell. Now, how do these intricate cellular cities come together to build something as complex as a human body? In Module 2, the 4 basic tissue types, nature's building blocks, we're going to discover a profound simplicity. Despite the incredible diversity of organs, all of them are constructed from just 4 fundamental tissue types. Just 4.
Yeah, it's quite amazing when you think about it. It really drives home how foundational this module is. Understanding these 4 types is like learning the alphabet before you read a complex novel. It's the absolute basis of all organ-level anatomy and pathology, giving you a fundamental language for medicine.
Okay, let's start with epithelia, the body's linings and barriers. At its core, epithelia are continuous sheets of cells that cover all body surfaces and line all body cavities. Conceptually, they are like the tiles and wallpaper of the body, smooth, patterned, sometimes layered, and always separating inside from outside.
The interface tissues.
Exactly. They're the interfaces, the front lines.
Their functions are incredibly diverse. Protection, skin, secretion glands, absorption intestine, and acting as a vital immune barrier. A key feature is the basement membrane, a thin but tough carpet underlay that anchors epithelia. Epithelial cells also have a high turnover rate. Your skin renews every, 28 days, your gut lining every 3 to 5 days.
Wow, that's fast.
It is. This rapid regeneration is crucial for protection, but clinically it also means epithelial tissues have a high risk of cancers, called carcinomas, because frequent cell division increases the chance of mutations.
And we classify epithelia by the shape of their cells and the number of layers, which helps us understand their specific jobs. Simple squamous, thin, flat cells, fried egg appearance for rapid exchange and low friction. Think thin glass tiles in lung alveoli or blood vessel linings.
Like endothelium.
Right. Simple cuboidal, cube-like cells for lining and modest secretion found in kidney tubules. Simple columnar, tall rectangular cells for absorption and secretion abundant in the GI tract. Stratified squamous, multiple layers for abrasion resistance. This comes in keratinized, like your skin's waterproof outer layer, thick ceramic tiles, and non-keratinized, moist surfaces like the mouth.
Protecting against wear and tear.
Yep. Pseudostratified ciliated columnar appears layered, but isn't, often with cilia, motile hairs for moving mucus, and goblet cells secreting mucus, essential in the respiratory tract. Transitional epithelium, urothelium. Unique to the urinary system, these cells change shape to allow stretching without leaking. Imagine them as stretchy rubber tiles in the bladder.
very specialized. Beyond these basic classifications, you'll also spot specializations. Microvilli are tiny finger-like projections that dramatically increase surface area for absorption, like in the intestine.
More area, more absorption.
Precisely. Clinically in celiac disease, villus atrophy leads to malabsorption. Cilia, those hair-like structures, beat to move mucus and particles, crucial in the respiratory tract. Loss of cilia in smokers impairs clearance, increasing infections.
That makes sense.
And goblet cells secrete mucus, often found with ciliated epithelium. Excess mucus can cause obstruction, as in chronic bronchitis.
It's vital to remember that when these critical linings fail, it can lead to serious problems like infection, ulcers, or cancer. For example, in Barrett's esophagus, normal esophageal lining is replaced by columnar epithelium, dramatically increasing the risk of adenocarcinoma.
A dangerous switch.
And diagnostically, when tumor cells breach the basement membrane, that's a definitive sign of invasive carcinoma.
Epithelia are truly the body's linings and coatings. Their shape and layers dictate their function, and their specializations are key adaptations. When these crucial linings falter, it sets the stage for a range of pathologies, from infection to cancer.
Next up is B connective tissue, including adipose, the body's scaffolding and glue. The core concept here is that connective tissue is everywhere the most abundant tissue type. Unlike epithelia, its cells are scattered within a vast extracellular matrix, or ECM. I like to think of it as the scaffolding and bubble wrap of the body, giving support, flexibility, and cushioning.
That's a great analogy. It really captures its role. Its components are key to its function. You have cells, mainly fibroblasts, the builders that produce the extracellular matrix, ECM. The ECM itself has three main elements: collagen, providing incredible tensile strength;
What's wrong stuff?
elastin, allowing stretch and recoil; and ground substance, a gel-like material for support, hydration, and diffusion. This complex makeup allows it to bind structures, support organs, protect delicate tissues, and fill packing spaces.
We categorize connective tissue based on fiber arrangement. Loose areolar connective tissue, with its loosely arranged fibers, acts as packing material beneath epithelia.
Found pretty much everywhere.
Dense connective tissue is stronger. Dense irregular CT has a basket weave pattern for strength in multiple directions, like in skin dermis, while dense regular CT has parallel fibers for strength in one direction, like a rope or cable in tendons and ligaments.
Very ordered structure there. For fibers, remember tie-by collagen, which is the strongest, resists pulling forces. It's the steel rebar in concrete of dermis, bone, and tendons. Defects here cause osteogenesis imperfecta or brittle bone disease.
OA?
Right. Then there are elastic fibers, the coiled springs that allow stretch and recoil, found in skin and arteries. Their loss leads to wrinkles. Defects in their scaffold protein, fibrillin, cause Marfan syndrome, affecting the heart and joints.
Big systemic effects from one protein issue.
Absolutely.
We also can't forget adipose tissue, or fat. White adipose tissue stores energy, insulates, and cushions. Brown adipose tissue, rich in mitochondria, is specialized for generating heat, particularly important in infants.
Keeps babies warm.
Right. Clinically, adipose tissue plays a significant role in metabolic disease.
So when this complex scaffolding goes wrong, you see problems like hernias, joint sprains, and dermal aging. Genetic conditions like Marfan syndrome show how fundamental defects in connective tissue can have widespread systemic effects.
Connective tissue truly is the body's scaffolding, glue, and padding. When its delicate balance of cells and matrix is disrupted, the very structural integrity and flexibility of the body can be profoundly compromised. Now, let's explore sea blood and hematopoiesis, the body's transport system. The core idea here is to view blood as a specialized connective tissue that functions as the body's critical transport system.
Specialized connective tissue that sometimes surprises people.
Yeah, because it's fluid, right. But it fits the definition. It's a dynamic river of life, carrying oxygen, nutrients, immune defenses, and clotting factors throughout the body.
Indeed. All blood cells come from a common origin through hematopoiesis, the blood cell family tree. They're all formed from bone marrow stem cells. From these, we get the myeloid lineage, red blood cells, most white blood cells, platelets, and the lymphoid lineage, B, T, and NK cells for immunity.
Two main branches.
Exactly. Hematopoiesis also shifts during development, starting in the yolk sac, then liver spleen in the fetus, before settling in the bone marrow after birth.
So what are these key blood cells and their roles?
Red blood cells, RBCs, biconcave discs, enucleated, packed with hemoglobin for oxygen transport. They live about 120 days. Their production is regulated by erythropoietin, EPO, from the kidney in response to hypoxia.
Low oxygen triggers more RBCs. Yep. When hemoglobin breaks down, it's converted to bilirubin and excreted. Failure here leads to jaundice. White blood cells, WBCs, leukocytes, your immune defense. Neutrophils are the firefighters for bacterial infections. Lymphocytes, B cells, T cells, NK cells are crucial for adaptive immunity.
The smart immune cells.
Platelets, cell fragments for repair crews, essential for clotting and sealing leaks.
Understanding these blood cell lineages is key to diagnosing everything from anemia, low RBC hemoglobin, and various infections, WBC changes, to clotting disorders and blood cancers like leukemias. NK cells, for example, are crucial in early defense against viral infections and tumors.
So looking at a blood count tells you a huge amount.
A massive amount. It's a window into the body's status.
Blood is a vital, specialized connective tissue, a constant river of life and defense. All blood cells originate from a single stem cell family tree in the bone marrow, and their delicate balance is essential for life, reflecting how critical this transport system is for the entire body. Let's move on to cartilage and bone, the body's resilient frameworks. Part 1 is about cartilage. The big idea here is that cartilage is a supportive but flexible tissue, tough enough to hold shape, ears, nose, smooth enough to cushion joints, and light enough to be a model for growing bones.
Kind of the unsung hero sometimes. And it's unique because it's a vascular, no direct blood supply, and aneral, no nerves, meaning it heals very poorly.
That's a really important point clinically, isn't it?
Absolutely. Damaged cartilage, and it often doesn't recover well. It's made of chondrocytes and an ECM rich in type 2 collagen. Most cartilage has a perichondrium for nutrient supply, except at articular surfaces. We have 3 main types: hyaline cartilage, the most common, glass-like, for smooth joint surfaces and flexible support, slippery shock absorber, found in joints, trachea, and as an embryonic skeleton. Elastic cartilage, like hyaline but with elastic fibers for flexibility, bend and snap cartilage, found in the ear and epiglottis.
Makes sense for the ear.
Fibrocartilage, the toughest, with dense type I collagen for heavy loads, reinforced concrete, found in intervertebral discs and knee menisci. It lacks a perichondrium, making its repair even worse.
So if hyaline is our smooth glass and elastic is our bendy rubber band, fibrocartilage really is that reinforced concrete built for the toughest jobs.
Moving to part 2, bone. The core idea is that bone is living tissue, not just dead mineral.
People often forget that.
They do. It's highly vascular, innervated, and constantly remodeling. It has specialized cells, osteoblasts, builders, osteocytes, sensors, and osteoclasts, demolition crew. Its matrix is both organic, collagen for flexibility, and inorganic, hydroxyapatite for hardness. Compact bone form shafts, organized into osteons. Spongy bone is a lighter mesh found at ends of bones.
Bone biology directly connects to common diseases. Rickets osteomalacia, defective mineralization from vitamin D deficiency, and osteoporosis, reduced bone leading to fractures, show how delicate the balance of bone formation and mineralization is.
Yeah, disruptions have major consequences. Cartilage and bone provide the body's essential resilient frameworks, one flexible and avascular, the other mineralized and dynamic. Their intricate structure and remodeling are crucial for diagnosing and treating a wide array of skeletal pathologies.
Finally, in Module 2, let's look at E-muscle, normal microanatomy, the body's engines of movement. The big idea here is that muscle tissue truly is the engine of the body, with 3 distinct types: skeletal, cardiac, and smooth, each built differently, tuned for its role. This is a fantastic example of form follows function.
Absolutely. 3 engines for different jobs. Let's break down each engine type. 1. Skeletal muscle. These are very long, multinucleated cells with peripheral nuclei and prominent striations. They're packed with sarcomeres, the contractile units. You have fiber types built for endurance and others for explosive power. They contract voluntarily. Repair is limited by satellite cells. Major injuries often heal with fiber scar tissue.
So not great at fixing itself after big damage.
Not ideal, no.
So think of skeletal muscle as like a powerful sports car, fast, strong, but prone to engine damage if overstressed.
Next, 2. Smooth muscle. Found in the walls of hollow organs, GI tract, blood vessels, and controlled involuntarily. These are spindle-shaped cells with a single central nucleus, lacking striations. Contraction is slower, more sustained. Smooth muscle cells can divide and regenerate readily.
Better at repairs then.
Much better, yes.
Think of smooth muscle as the slow, steady engine, not flashy, but runs constantly without tiring.
Finally, 3. Cardiac muscle, found only in the heart. These are short, branched, striated cells, usually with 1 to 2 central nuclei. Crucial are intercalated discs, which mechanically anchor cells and allow electrical continuity, making the heart contract as one unit, a functional syncytium.
All beating together.
Exactly. Cardiac muscle has very limited repair capacity. Damage, like from a heart attack, is replaced by fibrous scar tissue, not new muscle.
Think of cardiac muscle as the hybrid car engine, rhythmic, efficient, built for nonstop running, but once scarred, it can't repair itself. This difference in repair capacity is why heart attacks heal with scars, not new muscle, leading to permanent functional loss.
A really critical point. Module 2 concludes by showing how these 4 basic tissue types form the structural and functional foundation of every organ. Later modules will link this directly to disease and repair, proving that this fundamental understanding is the bedrock of clinical medicine. Module 3, Clinical Relevance in Tissues. When form fails, function collapses.
Now we're moving on to Module 3, Clinical Relevance in Tissues. When form fails, function collapses. This is where normal tissue biology truly comes alive when we understand what happens in disease. This module is all about how abnormalities in bone, muscle, and skin lead to specific clinical problems, the core takeaway. Disease teaches us why normal tissue structure matters. When form fails, function collapses. It's an incredibly powerful concept.
This is where we bridge the gap from microscopic understanding to patient impact. Every symptom, every diagnosis can often be traced back to a fundamental disruption at the tissue level. It's the essential connection.
Let's start with A, bone diseases. Construction site gone wrong.
Okay. Bone is a living construction site where osteoblasts, bricklayers, build, osteoclasts, demolition crew, break down, and osteocytes, site managers, coordinate. Disease arises when this crew or the building materials go wrong.
The balance gets disrupted.
Exactly.
And when that happens, we see a range of key disorders. Osteogenesis imperfecta, OI, brittle bone disease. A genetic defect in type I collagen, the main rebar, leading to brittle bones, frequent fractures, and often blue sclerae. Clinically, it's vital to differentiate from non-accidental injury in children. OI equals bad collagen, bricks weak.
A really important differential diagnosis.
Vitamin D deficiency causes rickets in children, soft, bowed bones, and osteomalacia in adults, fragile bones, due to defective mineralization. Bad mineral, cement missing. Osteoporosis, reduced bone mass leading to fragility fractures, spine, hip. Risk factors include age, low estrogen. Imagine an old sponge full of holes, weak and crumbly.
Very common, especially post-menopause.
Achondroplasia. Mutation in FGFR3 gene causing abnormal endochondral ossification, resulting in short-limb dwarfism, like building a tower with short Lego pieces. Paget's disease. Disorganized, excessive bone remodeling, creating thickened, irregular, and weak bone in the elderly. Workers building a wall in a rush without measuring properly.
Leads to bone pain, deformities. This module truly explains why brittle bones and OI can be mistaken for child abuse, and why vitamin D deficiency affects children and adults differently, underscoring the importance of understanding the underlying cellular and tissue pathology.
Bone is a vibrant, living construction site, always being built and remodeled. If the materials are faulty or the crew isn't working properly, diseases emerge, powerfully illustrating how structural failures lead to devastating functional consequences. Let's move on to B, muscle disorders, engines misfiring. The core concept here is that muscle tissue is the engine of the body. If used, it grows, hypertrophy. If unused, it shrinks, atrophy. But when injured or diseased, it can misfire, stall, or even break down.
Use it or lose it, basically.
Pretty much. Skeletal, smooth, and cardiac muscles each respond differently to stress and injury.
This leads to a variety of key disorders. Atrophy, shrinking engine. Decrease in muscle size from disuse, immobilization, denervation, or aging, sarcopenia. Like a bike left in the shed, if you never ride it, it rusts and weakens. Hypertrophy and hyperplasia. Skeletal muscle only hypertrophies. Fibers get bigger. Smooth muscle can both hypertrophy and undergo hyperplasia. Cells multiply, as seen in pregnancy.
So smooth muscle is more adaptable in that way?
Yes, definitely. Regeneration. Skeletal muscle has limited repair, scar tissue. Smooth muscle has good regenerative capacity. Cardiac muscle has very limited repair. Damage, myocardial infarction, is replaced by fibrous scar tissue, not new muscle.
That point again about the heart scar, crucial.
It is. Muscular dystrophies, for example, Duchenne DMD, genetic defect in dystrophin, which stabilizes the muscle cell membrane. Without it, the membrane tears during contraction, leading to degeneration and weakness. Like a car with a broken belt in the engine.
Progressive and devastating.
Neuromuscular transmission disorders, faulty wiring, myasthenia gravis. Autoimmune disease blocking acetylcholine receptors at the neuromuscular junction, NMJ, causing fluctuating weakness. Spark plugs don't fire properly. Botulism. Toxin blocks acetylcholine release at NMJ, causing paralysis, cutting the ignition wire.
This section powerfully demonstrates why heart muscle cannot regenerate after infarction, leading to permanent scarring and functional loss. It connects microscopic defects to profound clinical challenges.
Muscles truly behave like engines, strengthening with use, weakening with disuse. But diseases can affect their structure, activity, or crucial nerve signals. Understanding these distinctions is paramount as it dictates prognosis and treatment.
Next, let's turn our attention to see the skin, the body's compromised armor. The core concept here is that skin, our largest organ, is fundamentally your suit of armor and primary interface with the world. It's a vital barrier, provides sensation, helps with thermoregulation, and even social signaling.
It does so much more than people realize.
Yeah.
Absolutely. The skin has distinct layers. The epidermis is the outermost epithelial layer, primarily keratinocytes forming protective layers, plus melanocytes for UV protection and immune cells. Beneath that is the dermis, a connective tissue layer with collagen, elastin, blood vessels, and nerves, providing strength and elasticity. Finally, the subcutis, hypodermis, is fat and loose connective tissue for insulation and cushioning.
Layers upon layers of protection and function.
Yes.
And when this armor is compromised, we see a wide array of clinical disorders, inflammatory disorders, like psoriasis, where overactive keratinocyte turnover leads to scaly plaques,
Thickened red skin patches.
pigmentary disorders, melanoma, malignant tumor of melanocytes, or vitiligo, autoimmune destruction of melanocytes, barrier defects, blistering diseases like epidermolysis bullosa, often due to faults in the epidermis-dermis junction or keratin mutations.
Really fragile skin. It's vital to remember that skin disease often has a major psychosocial impact, even when medically minor. Visible conditions can cause profound distress and isolation, highlighting that the skin is not just a biological barrier, but also a social interface.
That's such an important point. The emotional burden can be huge.
Absolutely huge.
This segment highlights the visible and hidden impacts of skin conditions on patients, demonstrating that understanding the skin's intricate biology is key to treating both the physical symptoms and the often overlooked psychological burdens.
The skin is a resilient suit of armor, a complex organ performing vital barrier, sensory, and regulatory roles. When any of its layers or cells malfunction, it not only compromises protection, but can profoundly affect an individual's well-being. Module 4, Membranes and Excitability. The body's communication network.
All right, let's shift gears now to Module 4, Membranes and Excitability, the body's communication network. This is where we really zoom in on how cells, especially neurons and muscle cells, communicate, both electrically and chemically.
Getting into the signaling now.
Exactly. The overarching takeaway here is that membranes and excitability transform cells into communicating networks that drive every heartbeat, every thought, and every movement. It's truly incredible.
This module builds on our understanding of basic cell structure, bridging the gap to systems physiology. It's about how the smallest parts generate the most complex functions in the body. Let's begin with A-cell membranes. Guarded borders. We've already discussed the plasma membrane as the cell's city wall, but here we emphasize it as a highly sophisticated guarded border. It features selective channels, gates, pumps, and receptors that meticulously control the cell's internal environment and allow for precise communication.
Selective permeability is key.
Absolutely fundamental.
This membrane acts as a selective border checkpoint with different lanes for molecules. Passive diffusion. Molecules move directly through the lipid bilayer down a concentration gradient, EGAU-CRO. Pedestrians walking straight through without barriers. Facilitated diffusion. Requires carrier proteins or gated ion channels, triggered by ligand voltage or gap junctions, but still moves down a concentration gradient, for example, glucose transporters.
Needs help, but no energy cost.
Right. Active transport. Requires energy, ATP or ion gradients, to move molecules against their concentration gradient. The classic example is the NO-CO AT-PACE pump, which uses ATP to pump 3 Na out and 2 Co in. This is the battery charger of the cell, essential for action potentials and cell volume.
Uses a huge amount of the body's energy, that pump.
Really? I didn't realize it was that much.
Yeah, up to 70% in the brain, apparently.
Wow. Co-transport. Simultaneous movement of 2 molecules, either in the same direction, symport, or opposite directions, antiport.
We should also briefly mention gap junctions, which are crucial for synchronizing electrical activity in the heart and smooth muscle by allowing direct cytoplasmic connections.
Like little tunnels between cells.
Exactly.
And clinically, these membrane functions have huge implications. Remember hereditary spherocytosis. That's a cytoskeletal defect beneath the membrane, showing how weak scaffolding equals fragile walls, city crumbles.
Back to that example, yes.
Many drugs like furosemide target ion channels, highlighting their importance in regulating electrical activity. Even adhesion molecule defects can be connected to cancer spread, where loss of cell adhesion allows tumor cells to detach and metastasize.
So membrane integrity and function are vital. The cell membrane is a highly selective dynamic border checkpoint. Understanding its intricate composition and sophisticated transport mechanisms is fundamental to grasping how cells maintain homeostasis, respond to signals, and how malfunctions lead to a vast array of clinical diseases.
Next, let's talk about B action potentials, electrical domino runs. The core concept here is that action potentials, APs, are rapid, all or none electrical signals generated by excitable cells, think neurons and muscle cells. These are absolutely fundamental to their function. Action potentials are like a domino effect or stadium wave, all or none, and self-propagating.
The fundamental electrical message. So, how does this electrical domino run actually happen? It's a rapid sequence of events. First, at resting potential, our cell is negatively charged inside, almost like a charged battery.
Primed and ready.
Exactly. When it gets a signal and reaches threshold, voltage-gated ion channels open. This leads to depolarization as sodium ions rush in, making the inside positive, lighting that spark. But just as quickly, sodium channels inactivate and potassium channels open, causing repolarization as potassium ions flow out, bringing it back to negative. Then comes a brief hyperpolarization, where it dips slightly more negative than rest before returning to normal.
Up, down, and a little dip.
That's the basic shape, yes. Crucially, after firing, there are refractory periods. The absolute refractory period is when another AP cannot be generated, ensuring unidirectional conduction. The relative refractory period requires a stronger stimulus. Like a stadium wave, each section needs time to reset before it can wave again.
Prevents signals going backwards.
Essential for proper function.
And how these APs get around is also crucial. This is propagation. In unmyelinated axons, they propagate continuously. But in myelinated axons, we see saltatory conduction, where the AP jumps between gaps in the myelin called nodes of Ranvier.
Much faster.
Right, much faster and more energy efficient. This whole process culminates in synaptic transmission, where the AP causes neurotransmitter release to communicate with the next cell.
The clinical relevance here is vast. Local anesthetics like lidocaine, blocked voltage-gated ion channels preventing pain signal.
Numbing the nerve.
Yes. Diseases of excitability include epilepsy and arrhythmias, where uncontrolled AP firing occurs. Many antiarrhythmic drugs target ion channels. Demyelination, as in multiple sclerosis, involves loss of myelin, slowing conduction, or blocking messages entirely.
Huge impact on function.
Massive.
Action potentials are the fundamental language of our excitable cells. Understanding this intricate domino run of ion movements reveals how messages are sent throughout the body and why disruptions can lead to conditions ranging from numbness to seizures.
Building on that electrical communication, let's explore C nervous system organization, wiring and switchboards. We can introduce the nervous system as the body's entire electrical wiring and computer system. It's the master controller, responsible for everything from movement and sensation to thought and automatic functions.
The central command, and it has two main divisions. The central nervous system, CNS, with the brain and spinal cord, is the main computer and central wiring hub. The peripheral nervous system, PNS, all nerves outside the CNS, are the cables running to and from the body,
bringing signals in and out.
Functionally, the sensory afferent division carries information to the CNS, while the motor efferent division carries commands from the CNS. The motor side includes the somatic system for voluntary control and the autonomic system for involuntary functions.
In the CNS, gray matter contains neuron cell bodies, the processing centers, like switchboards. White matter consists of myelinated axons, insulated cables for fast signal transmission.
Processing versus transmission.
Essentially, yes.
The CNS is so vital it has triple protection. First, the meninges, pia, arachnoid, dura mater are three protective layers.
The coverings.
Second, cerebrospinal fluid, CSF, cushions the brain and spinal cord like shock absorbers. And third, the blood-brain barrier, BBB, formed by tight junctions, selectively filters what enters the brain like airport security.
Extremely selective. Neurons are the wiring units, but they don't work alone. Glial cells are the essential support crew, the technicians, cleaners, and insulation specialists. In the CNS, oligodendrocytes form myelin. In the PNS, Schwann cells myelinate axons.
Different cells doing the same job in different places?
Right. One oligodendrocyte can myelinate multiple axons, while one Schwann cell wraps around only one segment of one axon.
Clinically, demyelination, as in multiple sclerosis, CNS, or Guillain-Barré syndrome, PNS, leads to slowed or blocked messages. CNS bleeds like subarachnoid hemorrhage from a ruptured aneurysm or epidural hematoma after trauma are critical events. Dermatome maps are clinically useful for localizing spinal cord injuries.
Knowing which area of skin corresponds to which nerve root. The nervous system is the body's sophisticated electrical wiring and computer system. When the wiring phrase, demyelination, or its multi-layered protection fails, bleeds, the entire system malfunctions, powerfully highlighting the interconnected roles of neurons and their glial support staff.
And that sophisticated wiring network has an automatic gearbox, too, the autonomic nervous system, ANS. This system runs all the involuntary functions in your body. Think of the sympathetic as the accelerator and the parasympathetic as the brake.
Keeps everything running in the background. The sympathetic nervous system, the accelerator, fight or flight, prepares the body for stress, increasing heart rate and blood pressure, diverting blood to muscles, bronchodilation, and pupil dilation. It's like pressing down the gas pedal hard to escape danger.
Getting you ready for action.
The parasympathetic nervous system, the brake, rest and digest, promotes maintenance and recovery. Slowing heart rate, stimulating digestion, urination, and glandular secretions. It's like applying the brake and idling the car, cools down, refuels, repairs.
Time to chill and recover.
Exactly.
These two systems communicate using different keys and locks, or neurotransmitters and receptors. Acetylcholine, ACH, is key for voluntary muscle and preganglionic ANS. Noradrenaline, NA, is primarily used by postganglionic sympathetic neurons, while aceate is used by postganglionic parasympathetic neurons. Different receptor subtypes, like alpha and beta adrenergic receptors, lead to different effects.
Different keys open different locks, causing different actions. Clinically, targeting these receptors is a cornerstone of pharmacology. Salbutamol, Ventolin, a V-swing agonist, relaxes airway smooth muscle for asthma relief.
Opens the airways.
Beta blockers reduce heart rate and blood pressure. Anticholinergics increase heart rate and reduce secretions.
So many drugs work on the ANS.
A huge number. It's a major target.
The autonomic nervous system runs the body's vital functions without conscious thought, constantly balancing the accelerator and brake systems. Understanding its neurotransmitters and receptors is critical, as many medications directly target these keys and locks to fine-tune our body's internal operations.
Module 4 builds the bridge between cell biology and systems physiology. It equips you to understand how cells generate and propagate signals, how these signals integrate in the nervous system, and how disruptions cause disease. We've seen how cell membranes are guarded borders, action potentials are all-or-nothing dominoes, the nervous system is a complex wiring network and switchboards, and the autonomic NS is an automatic gear shift. Together, these mechanisms govern every heartbeat, thought, and movement. Module 5, Internal Linings in Early Development. From Origin to Organization.
We're now into Module 5, Internal Linings in Early Development, from Origin to Organization. This module is going to zoom out first to the whole body, internal linings, and then we're going all the way back to early development and our embryonic origins.
From the big picture linings back to the very beginning.
Exactly. The powerful takeaway here is that the embryo lays down tissues and linings that persist into adult anatomy and pathology. It's truly amazing how those first few weeks of development set the stage for our entire lives.
This is where we really connect the dots between how our body is built, layer by layer from its very beginning, to how those foundational structures define our adult anatomy and vulnerabilities to disease. Let's begin with A, internal surfaces, wallpaper, Teflon, and anchors. The core concept is that your body isn't just organs floating in space. Everything is lined, wrapped, or anchored by special coverings.
Right.
We can use the analogy of a house. The walls have wallpaper, mucosa. The moving parts like doors and windows has slippery hinges, serosa, and the fixed beams are held with braces, adventitia.
Okay, first we have mucous membranes, mucosa, the indoor wallpaper. These line open internal cavities connected to the outside world, respiratory digestive tracts. They consist of an epithelium, basement membrane, lamina propria, loose connective tissue with immune cells, security guards, and muscularis mucosae.
That little muscle layer helps it move.
They maintain moist, lubricated surfaces, secrete mucus, and act as an immune barrier. Clinically, inflammatory conditions like Crohn's disease affect the gut mucosa, and damage to the basement membrane can lead to ulcers.
Contrast those with serous membranes, serosa mesothelium, the Teflon coating. These are found in closed body cavities, pleura, pericardium, peritoneum. They are thin, smooth linings that crucially reduce friction, allowing organs to glide smoothly. Scares heart beating, lungs inflating.
Super important for movement.
Absolutely. Clinically, conditions like pleural effusion, fluid between layers, cause breathlessness, and pericarditis, inflamed pericardium, cause a sharp chest pain due to increased friction.
And finally, for organs that don't need to slide around, we have adventitia, the bolts, and duct tape. This is a layer of connective tissue that firmly anchors organs in place where movement isn't required, like duct tape or bolts that fasten pipes to the wall. An example is the esophagus in the chest.
Holds things steady. Understanding the body's internal surfaces, mucosa, serosa, and adventitia, is key to comprehending organ protection, movement, and interaction. This knowledge provides the basis for diagnosing conditions involving fluid accumulation, friction, or inflammation in various body cavities.
Let's take an even bigger step back to pre-embryonic period in gastrulation, the layer cake moment. Human development starts incredibly simply, tracing the journey from fertilization to the formation of the three primary germ layers. Gastrulation is truly the layer cake moment of development where a flat disk of cells generates all tissues.
A pivotal moment, indeed. It starts with fertilization, zygote, then forms a morula, then a fluid-filled blastocyst with an inner cell mass that becomes the embryo. By days 7-12, this forms a bilaminar disc. Then comes gastrulation around days 13-14, the blueprint formation. Cells migrate inward through the primitive streak, creating the layer cake of the embryo, ectoderm. The outer layer forming skin, epidermis, nervous system, brain, spinal cord. Mesoderm, the middle layer forming muscle, bone, connective tissue, blood, kidneys. Endoderm, the inner layer forming the lining of the gut, liver, pancreas, lungs.
All tissues trace back to one of these three.
Fundamentally, yes.
Clinically, mistakes here lead to serious developmental problems. Ectopic pregnancy is when the blastocyst implants outside the uterus. Teratomas are tumors with multiple tissue types because they arise from abnormally persistent germ cells.
Contains things like hair and teeth sometimes.
Yeah, bizarre but explained by development.
From a single zygote, a complex layer cake of germ layers is meticulously formed during gastrulation. This process creates the fundamental blueprint for every tissue and organ, highlighting the critical importance of these early developmental steps.
Moving on, we have C, establishment of the body plan. Embryonic origami. This is where the truly remarkable transformation occurs. The flat trilaminar disc morphs into a 3D tube-shaped body. This happens through complex folding and the emergence of vital scaffolding structures, truly embryonic origami.
From flat sheet to body tube. Central to this is the notochord, a rod of mesoderm that induces the overlying ectoderm to form the neural tube, brain and spinal cord, establishing the body's central axis. It acts like a conductor directing the embryonic orchestra.
Setting up the main axis.
Yeah, that is it.
Then we have the somites, the Lego blocks of the embryo. These paired blocks of mesoderm form segmentally and differentiate into the dermatome, dermis of skin, myotome, skeletal muscle, and sclerotome, vertebrae, ribs. Somites are like the Lego blocks of the embryo, precisely building the segmented structures.
Explains our segmented body plan like vertebrae and ribs. The complex process of folding between day 22-28 transforms the flat disc into a 3D tube. Longitudinal folding creates the head-tail ends and primitive gut. Lateral folding brings the sides together, closing the body wall and surrounding the gut.
Kind of like rolling up the sheet of paper.
A bit like that, yes. It puts ectoderm outside, endoderm inside, gut lining, and mesoderm in between.
Clinically, failures in this intricate process lead to significant developmental defects. Neural tube defects, NTDs, like spina bifida, failure of caudal closure, often preventable with folic acid, or anencephaly, failure of cranial closure, lethal, are prime examples.
Shows why folic acid is so important pre-conception.
Absolutely. Dermatome maps become incredibly useful for localizing spinal cord injuries later in life.
The intricate choreography of embryonic folding and the precise development of structures like the notochord and somites lay the very foundations of our adult anatomy. Understanding this embryonic origami is essential for appreciating both the marvel of development and the origins of many congenital pathologies.
Module 5 takes us from the fundamental linings that protect our internal organs to the earliest, most delicate stages of our embryonic origins. These principles aren't just fascinating developmental biology, they are the genesis of all adult anatomy and pathology, reminding us that form and function are sculpted from the very first moments of life. Module 6, histopathology and disease mechanisms, how tissues fail and repair. Welcome to Module 6. Histopathology and disease mechanisms, how tissues fail and repair. This module marks a critical bridge, connecting all the normal tissue biology we've explored to the realities of disease.
Bringing it all together.
We'll delve into histopathology, the microscopic study of diseased tissue, and unravel the core mechanisms by which cells and tissues adapt, become injured, repair themselves, or, tragically, progress to cancer. The overarching takeaway is understanding why chronic irritation, like smoking, can lead from metaplasia to dysplasia and, eventually, cancer.
This is where all the foundational knowledge from previous modules culminates. Understanding how cells and tissues respond to stress, injury, and uncontrolled growth is the essence of pathology and ultimately clinical diagnosis. It's where the rubber meets the road. Let's start with A, Introduction to Histopathology, mapping the damaged city. Histopathology is, quite simply, the gold standard for diagnosing disease. By examining structural changes in tissues under the microscope, it tells us what has gone wrong.
The definitive answer often comes from path.
Very often, yeah.
To really grasp it, it's helpful to distinguish it from related disciplines. Histology is the study of normal tissue, the architect's drawings of a perfect house. Histopathology is the study of diseased tissue, seeing where the house has cracks, leaks, or broken windows. Cytology is the study of individual cells, like a pap smear, looking at one brick under a magnifying glass.
Different levels of looking. Preparing a tissue specimen involves a meticulous sequence: biopsy, fixation to freeze the tissue in time, embedding in wax, sectioning into thin slices, and finally staining, like H&E, to highlight structures. We also use frozen sections for rapid intraoperative diagnosis, a quick sketch map during surgery.
To guide the surgeon right then and there.
Exactly.
Why does histopathology matter so much? It's indispensable. It provides definitive diagnosis, grading, and staging of tumors, identifies inflammation and infections, and shows evidence of repair. Without histopathology, cancer treatment is like fighting blind.
You need to know what you're treating. Histopathology is the critical lens through which we view disease. It transforms raw tissue into a map of a damaged city, providing invaluable insights that are the cornerstone of accurate diagnosis and effective clinical decision-making.
Now let's explore B, cellular adaptations to stress, survival tricks. Cells constantly face stress. If it's mild, they use survival tricks to adapt. These changes are often reversible, but can, if prolonged, predispose to disease. Think of cells like people in a city under pressure.
Trying to cope. These adaptations are vital but have limits. Hypertrophy cells get bigger, increase in cell size to cope with increased workload, e.g. cardiac muscle and hypertension, skeletal muscle after training. Workers get stronger and bulkier. Hyperplasia cells increase in number, increase in cell number via division, an example endometrial hyperplasia, callus formation. More workers are hired. If abnormal, can predispose to cancer.
So hyperplasia can sometimes be risky.
It can be if it becomes unregulated. Atrophy cells shrink or disappear. Decrease in cell size or number due to reduced demand. For example, muscle wasting in a cast. Workers shrink or are laid off. Metaplasia cells change type. One differentiated cell type is replaced by another better suited to persistent stress. For example, respiratory epithelium in smokers or Barrett's esophagus in reflux. Workers change profession entirely. Clinically, metaplasia increases cancer risk.
That's a really key one for cancer development.
Very key. It's often a precursor step.
It's crucial to remember that these are generally reversible if the stress is removed. However, persistent stress can push cells beyond adaptation, down a dangerous path toward irreversible injury, precancerous changes, or even organ failure.
Cells are masters of adaptation, constantly trying to survive. But these survival tricks have limits. Persistent stress can push cells beyond adaptation, down a dangerous path toward irreversible injury, precancerous changes, or even organ failure. Understanding these responses is key to understanding disease progression.
Moving beyond adaptation, let's look at C, cellular injury. Beyond adaptation, if stress is stronger than a cell can adapt to, it can be injured, leading to either reversible injury, recovery possible, or irreversible injury, cell death. Think of it like a city hit by a storm.
The breaking point.
In reversible injury, stunned but can recover, the cell is temporarily damaged but can recover. We often see cellular swelling, failure of ion pumps, and fatty change, lipid accumulation common in the liver. Reversible injury is like a power cut. The city powers down but can restart.
If you remove the stressor in time, but if the damage is too great, the cell dies. This is irreversible injury. We differentiate between two main forms of cell death: necrosis messy, uncontrolled cell death, caused by hypoxia, toxins, trauma, characterized by cell swelling, membrane rupture, and leakage of contents, triggering inflammation. Necrosis is like a house explosion, debris everywhere, neighbors upset.
The inflammatory response is key there.
Absolutely. apoptosis programmed, tidy cell death,
Huh?
a controlled programmed process involving cell shrinkage and fragmentation into apoptotic bodies, which are tightly removed without inflammation. Vital in normal development and removing old infected cells. Apoptosis is like a planned demolition workers clear debris quietly.
Clean and controlled. Under the microscope, irreversible injury shows a sequence of nuclear changes. Patenosis, nucleus shrinks and darkens. Kuryorexis, nucleus fragments. And karyolasis, nucleus dissolves. Remember, PKL, shrink, shatter, lose.
Visual clues to cell death. Clinically, ischemic infarction, e.g. heart attack, leads to necrosis. Viral hepatitis often shows apoptosis. Distinguishing between messy necrosis and tidy apoptosis is not just academic. It underpins how we interpret disease and formulate treatments.
From reversible cellular swelling to the irreversible finality of cell death, understanding these mechanisms is foundational. Distinguishing between messy necrosis and tidy apoptosis is not just academic. It underpins how we interpret disease, from heart attacks to viral infections, and how we formulate treatments. Let's turn to de-inflammation and repair. Firefighters and builders. Inflammation is the body's fundamental response to injury. We can frame it. Acute inflammation equals firefighters rushing to a blaze. Chronic inflammation equals a construction crew working on long-term repair, sometimes leaving too much scar tissue.
A good way to think about the two types. Acute inflammation. Rapid onset, characterized by vascular changes, redness, heat, swelling, and neutrophils migrating to the site, often forming pus. Can lead to resolution, abscess, or progression to chronic.
The immediate response team.
Exactly. Chronic inflammation, longer duration involving lymphocytes and macrophages, often leads to tissue destruction, repair attempts, and fibrosis, scar tissue.
The long, drawn-out battle.
Can be, yes.
Yeah.
Often causing more damage over time.
And after inflammation, the body tries to rebuild, which is repair. Regeneration is the ideal. Restoration of normal tissue and function by cell proliferation, example liver regeneration, requiring an intact ECM scaffold. Fibrosis scar formation replaces lost tissue with collagen-rich scar tissue when damage is severe or regeneration is limited. For example, heart attack healing with a scar, not new muscle.
Patching it up rather than rebuilding perfectly. This explains why heart attacks heal with scars, not new muscle. The balance between inflammation, the body's firefighters, and repair, the builders, dictates whether normal function is restored or permanently lost.
Inflammation is the body's essential response to injury. Its acute phase is rapid defense, while chronic can lead to prolonged damage. The subsequent repair, whether by perfect regeneration or by fibrosis, profoundly impacts long-term function and is a cornerstone of understanding disease progression and healing. Finally, let's get a crucial neoplasia preview. Building codes failure. The big picture here is that neoplasia is fundamentally abnormal, uncontrolled cell growth, which occurs when the city's building codes fail.
Growth gone wrong. That's a perfect analogy. We contrast normal cells as well-regulated builders with neoplasia, as builders who keep constructing without permission, sometimes destroying neighboring structures. We classify tumors into two categories. Benign tumors, slow-growing, well-differentiated, localized, often encapsulated. They do not invade or metastasize.
Generally stay put.
Malignant tumors, cancer. Rapid, uncontrolled growth, poorly differentiated, invade surrounding tissues, and can metastasize, spread via blood lymph.
The dangerous ones.
Yes.
We differentiate malignant tumors by their tissue origin. Carcinomas arise from epithelial cells, for example, skin linings, while sarcomas arise from mesenchymal tissues, bone, muscle.
Different origins, different names. Understanding the progression from dysplasia to invasive cancer is crucial. Dysplasia is abnormal, disordered cell growth, potentially reversible. Carcinoma in situ is severe dysplasia across the full epithelium but has not breached the basement membrane. Invasive cancer is when tumor cells cross the basement membrane and infiltrate underlying tissue, the hallmark of malignancy, allowing access to blood vessels for metastasis. That basement membrane is the critical line. It really is. Crossing the city walls, the tumor can now spread beyond local control.
This is crucial for early detection. A cervical smear can detect dysplasia before invasive cancer. Understanding this progression is paramount for diagnosis and treatment.
Module 6 brings us full circle, from normal tissues to how they fail. We've introduced how we look at diseased tissue, histopathology, how cells adapt, get injured, and die, how the body responds and repairs. And finally, a preview of neoplasia, the breakdown of growth control. This knowledge is not just academic. It's the foundational language for every pathology you will encounter. Outro.
So what does this all mean? We've just taken an incredible deep dive, starting with the miniature cities of our cells, moving through the 4 fundamental tissue types, exploring how they falter in disease, communicate through electrical signals, take shape in early development, and finally, how they are examined in pathology.
Quite the journey.
It's been a journey from the invisible to the intensely clinical, designed to be your essential course in tissues of the body.
You've gained a comprehensive framework, not just isolated facts. You've seen how everything is interconnected, constantly adapting and responding. This isn't just about memorizing terms. It's about developing the structural and functional thinking essential for every clinician.
Thinking like a doctor.
Exactly. Giving you the why and how, behind the body's intricate design and its vulnerabilities to disease. Our goal is to make this complex subject understandable and truly retainable.
We wanted to give you a shortcut to being genuinely well-informed, packed with aha moments, and a pace that respects your time, preparing you to tackle the complexities of medicine with clarity and confidence.
As you continue your medical journey, consider this. Every single disease, from the common cold to the most complex cancer, ultimately manifests as a dysfunction at the cellular and tissue level. The real mystery for you as a future doctor isn't just what the disease is, but where and why those fundamental building blocks began to falter, and how you might intervene to restore their intricate balance.
A lot to think about there. Stay curious, keep exploring, and we'll see you on the next Dip Dive.